In the last session, we were discussing about robot dynamics. Robot dynamics. So robot dynamics, it is very important because whenever we do optimization, for example, in a redundant manipulator which has greater degrees of freedom to do a particular task, in such cases, we have infinite solutions or infinite trajectories to do a particular task. So in such cases, we have to choose the path that is energy efficient. So we have to choose the path that is energy efficient. So how to find the energy efficient. So we have to do the dynamics to see what are the tasks that are required to move the manipulator along any particular trajectory. Supposing if you are having a manipulator, right? So we have to do the dynamics so that we can get the tasks that are required to move the manipulator along any particular trajectory and then see what is the energy expended. So in terms of control, to move the end effector in the particular trajectory, the controller must find what is the corresponding position, velocity and acceleration of the joints that is required in order to follow the trajectory. So in order to follow the trajectory, it has to do a torque control. Then it has to supply the required amount of torque so that the end effector moves with a particular position, velocity and acceleration. So when the velocity, as we know, the velocity and acceleration are propagating in this direction. So when they are propagating, they will cause the inertial forces to act on the links. So the force F which acts on the end effector, that will come backwards. It will come backwards. So the objective is to find the various forces acting on the system whenever the manipulator is moving and to find the torque. So we need to determine this torque which will balance out all the internal and external forces. Right. So this we have discussed in the uh, earlier session. So in this session, we will be deriving the dynamics of one DOF manipulator with point mass by using a Lagrangian Euler method. So let us consider a single link manipulator with the 1 degree of freedom. With 1 degree of freedom, let the length of the link be denoted as L and the joint angle to be theta. And here we are considering point mass. So the mass, let the mass be represented as small m here. So this is the point mass, right? So to derive the dynamics by using Lagrangian Euler method, we need to know the potential energy and kinetic energy. So the potential energy, as you know, potential energy is equal to mgh. So where m is the mass, g is the gravitational constant, and h is the highly weighted height. So here, if at all you have a link, single link with this angle theta and the length L. So this elevated height will be L sine theta and this adjacent side will be L cos theta. So we'll be getting the potential energy to be mg L cos theta. Sorry, mg L sine theta, right? Then we have to find the kinetic energy. The kinetic energy, we know it is half m into v square. So m is the mass and v is the velocity. So we know the position of the manipulator here at this point, that is x comma y. So which is L cos theta comma L sin theta. So given the position, we can obtain the velocity, that is the first order derivative of the position. So it would be minus L sin theta comma L cos theta into theta dot. So we want v squared here, right? So what would be v squared? V squared will be equal to x squared plus y squared. So that would be L squared theta dot square into sine square theta plus cos square theta, that becomes 1. So the v square will be equal to L square theta dot square. So we'll be getting half into m L square theta dot square. So this is the kinetic energy, right? So now we have to find the Lagrangian, which is L is equal to kinetic energy minus potential energy. So that is, we have already found the kinetic energy and potential energy. So just substituting the values, here we get half m L squared theta dot square minus the potential energy, that is mgl sine theta, right? So we'll be getting the torque equation. So torque equation, as we know, it is tau is equal to d by dt of dou L by dou theta dot minus dou L by dou theta. So let us, having known the Lagrangian, let us first find dou L by dou theta dot. So dou L by dou theta dot is equal to, so you have to differentiate this Lagrangian equation with respect to theta dot. So you have only theta dot in the first term only you have. In the second term, we don't have any theta dot here. So you want to just differentiate the first term alone. So you will be getting m into L theta, m into L square theta dot, ml square theta dot. So this is your dou L by dou theta dot, and then dou L by dou theta. So dou L by dou theta is equal to, so here the first term you don't have theta, so only in the second term you have theta. So differentiating, you will be getting dou L by dou theta will be equal to minus mgl cos theta, right? So directly by substituting these values in the torque equation, so you tau is equal to d by dt of dou L by dou theta dot. So he will have dou L by dou theta dot as ml squared theta dot. So uh, d by dt of dou L by dou theta dot will be ml squared theta double dot, right? Then plus mgl cos theta. So this is the dynamic equation for a single link manipulator or a one DOF manipulator, right?